Greetings, this is Ward Harriman, AE6TY. Today's topic is end-fed antennas. Before proceeding, I confess to having read WA7ARK's articles and so have some idea where this might be headed. I'm using the latest cook of SimNEC version 2.1. I hope to release this version to the general public in the next few days. Those familiar with SimNEC know that an antenna can be described using a combination of graphics and text. Let's get started. So here I have an empty design. SimNEC uses ruse blocks to describe antenna. Ruse stands for Really Ugly Schematic Editor. So here's a ruse block. Let's open it up. Do a little housekeeping. I'm going to move these down because I like to put my antennas at the top. An antenna is described using only these two symbols. An endpoint of a wire, which I could describe numerically, but I'm going to use variables. This is X, Y, and Z. And I'm going to copy this to over here. So now if I were to wire those together, I would have a wire between this place and this place. Now, as the common practice, I generally put all my variables at the top down here. This is not necessary, but I generally do. I'm going to have a length, I'm going to have a height, and I'm going to have what I want to call a tap point. So I'm going to put it in right now. So here I have a wire and I want to put a tap point in, and that will be at a percentage from here to here. In this case, it's going to be variable. Those unfamiliar with editing ruse blocks should probably go look at my other videos that shows how this is done. And I heartily recommend reading the manual because the video never uses all of the features. I try really hard to put all the feature descriptions into the manual. Continuing to wire things up. And there I have my basic antenna. It's already giving me some errors. And it's giving me a bunch of errors down here, some of which I know, for example, it won't like the zero length antenna. It doesn't mind a zero height, but I'll come back to that. And the tap point can't be zero, so I'm going to put it at 50. It's still got some errors. What do we got? Missing neck unit. So it doesn't know what the units are. This is the length of wires, and this is the diameter of wires, the units for the diameter of wires. And no errors. Let's go look at this antenna in space. That's done by bringing up the NEC display. SimNEC, like many programs, benefits from multiple screens, but if you don't have multiple screens, it works fine. I'm going to use it on one screen today so that I can do the video. Here's my ruse block description, and here's my antenna in space. I want to center it, so I'm just going to do a find. Here's my wire, and I can move this around kind of at will. So no surprise, looks like a dipole. There's no ground, so it's coming below ground. If I snap, you can see it's got an elevation that's negative, so I want to put in a ground. Typical numbers here. And there we have our typical dipole in space. We're going to want to play with an 80 meter dipole, so let's put in the length of 80 meters. Or or 40 meters for an 80 meter dipole. Again, this is what the field looks like. That's because we're running at 10 megahertz. Let's set this down to a reasonable frequency in the 80 meter band. And there we go. And this is what typically looks like when you have a low 80 meter dipole. So now that we have our basic dipole working, let's move on to multiband operation. Let's look at the Smith chart. I'll make this a little smaller. Put it down here, kind of out of the way. Let's look at the Smith chart. Let's do a sweep. And we can see here that we have our fundamental right over here and some higher order harmonics, and that's encouraging. What are those frequencies? Well, we can look at the SWR chart, and we'll see that there are some frequencies here. And if I turn on the bands, we find that the 40 meter band, the 20 meter band, the 15 meter band, and the 10 meter band are not covered. How can we get these harmonics to move around, or how can we introduce other harmonics? One of the ways we add other harmonics is to play with the feed point. Off-center fed antennas have the ability to bring in the even harmonics of our fundamental. 40 meters is going to be an even harmonic of 80. 20 is going to be an even harmonic. So we need to move the center tap point to bring in the odd harmonics. Now we can play with this. I'm going to set some limits on it so I don't accidentally move too far out of range. And let's just move it quite a bit to begin with. There's 40. And we're starting to see some other harmonics kick in. All right, here's 40 meters, here's 20 meters, here's 15 and 10. So we're starting to get harmonics kind of like where we want them to be, even with an off-center fed at only 40%. It turns out that there are other places where those harmonics will come into play. A typical number is, say, 30, and we're seeing 40 meters come in pretty handily. These are not too far off. That's high. These basically tell us that the antenna is too long or too short. Let's increase its length a little bit. And we're starting to see harmonics near all the interesting bands. Let's try some other places. Let's try a tap of like 10%. And here we have harmonics kind of everywhere we want them. Looking at it on the Smith chart, we see that all the harmonics are up here on the right. In order to move them over to the center, we probably just want to use a transformer. So I'm going to bring in a transformer. And typically in end-fed antennas, the ratio here is, say, 49:1. So I'm going to set these to be 49:1 impedance ratio. I like to draw it as an auto transformer. And typically with this kind of transformer, the common practice is to put in a capacitor as well, and let's go ahead and put that in. And that capacitor is usually about 100 puff. So how are we doing? Well, we got our antenna now appears to be a little too long, and so a little too short, so I'm going to make it longer. I'm just going to hit the up arrow button on the length. And here we have pretty good coverage on 40 meters, pretty good on 20, 15, and 10, all well below the 3-to-1 SWR. So what's the next step? Well, we want to move this 80 meter resonance up and leave the others alone. So if we want to do something at a low frequency and not at higher frequencies, we would either use a capacitor in series or an inductor in parallel. And in this case, it's tough to put a parallel inductor in the middle of an antenna, so we're going to want to put in a capacitor somewhere. Now, we all know that adding an inductor into an antenna will reduce the resonant frequency, but we often forget that installing a capacitor in the antenna will actually increase the resonant frequency. So a capacitor would increase this, and hopefully at the higher frequencies would have no substantial impact. So let's go ahead and put in that capacitor. Where should we put in that capacitor? Because we want it to work at 80 meters, and we probably don't want it to work at others. I'm just going to guess and say in the middle. So we want to put in a capacitor, which means we're going to need another one of these so we can wire something into the antenna. We might want to play with this, so I'm going to say C-tap. And we're going to need to add a capacitor. Of value. Okay. Now, the problem, of course, here is that it doesn't like tapping this here. I didn't specify the location. Let's go look at it on the NEC display. Here we have our wire, and I'm going to increase the gain on here. Notice that we have current on this side, but we don't have any current over here. And that's because the value of that capacitor is 0. Not a good value if we want to get anything across. Let's put it at 50 puff just to get started. Okay, so now we have our 50 puff capacitor in the middle. This is our current distribution. And it has, in fact, moved the 80 meter resonance well over. It's moved 40 or a little bit. It's moved the other frequencies not very much. So it's pretty much where we want it. Now we just need to adjust this. And we do that by playing with this value. Now 50 got it to be too high, which means the capacitor has too small a value. So I'm going to use the up arrow on my keyboard to tune this capacitor up a little bit. Notice over here that that point is moving. And that looks like about as well as I can do at this point. It's had some movement on the 40 meter bands, and on the others I could come and change this length a little bit. Of course, I'm going the wrong direction. So there I've played a little bit with the length. And maybe play with this a little bit again. No. Nope. So here's about as good as I can get by hand playing with the capacitance and the tap point. There's clearly some trade-off that's going on in here. We could move the trap point. I haven't played with it very much. That takes a long time to explore things in 2 dimensions. I'm going to use a feature of SimNEC that makes this a little easier. So I'm going to say I want to play with the tap point and the value of that capacitor. And let's do the tap point from, say, 15 to 90. Let's only do 50 points. Probably don't need more than that. And we're going to do a capacitance of, say, 10 puff to 500 puff. Don't need that. So here we have a plot varying those 2 parameters, and we see that if we were to pick this point right here, 80 meters would have an SWR of down in the 1.1 range. Let's pick it just to see what happens. I'm going to right click on this point and it's going to set the values. See that circle right there that says that's now the operating point. And let's go back and look at the SWR for the bands now. 80 meters is in fact pretty good. 40 meters is way messed up. The other 2 are fine. And 40 meters is messed up because where we put that capacitor and its value affect the current distributions. Putting it right here had an impact on the 40 meter resonance. So we would have a trade-off between the 80 meter band and the 40 meter band. And again, playing in 2 dimensions with 2 variables can take quite a while, especially the trade-off between the 2. Fortunately, SimNEC has a built-in optimizer, and while setting up that optimizer can be a little complicated at times, I don't want to drag you through it here. So I'm going to just bring up a design where I've already done that. Pay no attention to this. I want to optimize across a certain number of bands. So I'm going to try to optimize across all these bands, 80, 40, 20, 15, and 10. I'm just going to run the optimizer. This can take a while. I may edit it out. So here is what I get if I optimize across all of the bands. 80s, 40, higher bands are pretty good. Could do better here. 40 and 80 are not great. And it could be, because of the way I do the optimization, that the interest of these higher bands is confusing the lower ones. So I'm going to actually go and just optimize these 2, hoping that these fall in line as they seem to have been doing. So I'm going to change my bands. I'm not going to optimize these bands anymore. And now let's run the optimizer. All right, there it's done the optimization just on the 40 and 80 meter bands, and it's done pretty well on the other ones. Now, the optimizer actually did a couple of interesting things. Let's just take a quick look. You can see what's going on. The optimizer is actually optimizing the length of the wire, the place that I put the capacitor, the value of that capacitor, and the turns ratio of the transformer. You'll notice that the transformer is no longer 49 to 1. It's actually now 65 to 1. Let's put it back at 49 to 1 and see what happens. It's not awful. Let's run the optimizer not doing the transformer. Again, just 40 and 80, leaving the transformer alone. There, it's done. This is what I get leaving the transformer alone. It's actually a little bit better. This video is getting long enough. We've reached pretty much our goals. Everything's other 3 to 1, which is well within reach of anything with an internal transmatch, and probably good enough for most of the rigs anyway. So let's sum things up. What did we do? We got started out with a clean slate, and we added the antenna using a combination of graphics and text. We chose to build an 80-meter dipole, and we examined the harmonics. Finding essentially none of them useful, we started playing with the drive point, and we found that the drive point could give us harmonics at 15 and 28. We found several places where the harmonics were at all the bands of interest. We then looked at the Smith chart and decided that a transformer was probably needed. We added it using the widely used 49:1 ratio with the associated capacitor. We then adjusted everything interactively to get everything we wanted except the 80-meter band. We added a capacitor in the middle of the dipole, hoping to increase the resonant frequency of 80 meters. It had little effect on the higher frequencies, but it did affect the 40-meter band. We did some exploration of how and where to put the capacitor. Ultimately, we ran the optimizer on the 80 and the 40-meter bands together to achieve a workable solution across all bands. I hope this video demonstrates how SimNEC can be used to describe an antenna and how the interactive nature of SimNEC can be used to explore the design space. Special thanks to Dan McGuire, AC6LA, for all his suggestions and tireless testing of the more recent versions of SimNEC. Again, I hope to release this version of SimNEC to the general public in the next few days. This is Ward Harriman, AE6TY. Thanks for watching.